everyone. Welcome into lecture number 5 on Calculus 3. This lecture is going to be about functions of several variables. So let's start off by defining what we mean by a function of several variables. This would be a definition. And of course, a function of several variables is going to be a function itself. We'll draw a picture here in a moment, but a function of several or multiple variables is simply a function whose domain is a subset in Rn, n-dimensional space, and its range is a subset of R. So it takes points from n-dimensional space and assigns a number to each one. So we could write this again. The range might not be all of the real number set, but that would be the codomain. Whoops. But the range itself is a subset of the real number set. So what does this mean? Usually for us, our domains are going to be subsets of either R2, two-dimensional space, or three-dimensional space. And sometimes we will think of these as vectors, right? Vectors, sets of vectors as opposed to sets of points. So sometimes we'll think of these as follows, and so I'll write this in this following way. But let's say capital F here, it could be lowercase f, doesn't matter. But capital F maps, again, our domain D to the range R, but I'm going to write it just in terms of the number sets here. So Rn to R, all right? Or we could say that F maps Vn, the set of vectors, to R. And what's the difference? Well, the difference is just how we write down the formula, right? So let's suppose we're in three-dimensional space and our points have three coordinate spots, x, y, and z, then we could say that this is f of x, y, z, or we could say that this is f of x with a hat, where x with a hat represents the vector whose terminal point in standard position is the point, right? X, y, z. So we've done this before, but we'll continue to do it, right? Where we just kind of, when it's convenient for us and not too inappropriate, we will conflate the ideas of n-dimensional real space with n-dimensional vector space, right? Space of n-dimensional vectors. And so we'll write this out this way. Now, geometrically, what does it look like here? So in our previous studies up to this point, in the last 4 lectures, we've studied functions that take in one real number and give back a vector, right? And so this is going to be the exact opposite. So now what we're going to do is we suppose that we have a domain. I'll sketch this in three-dimensional space here, but we have our domain in x, y, z, three-dimensional space. And maybe the domain is just some kind of blob. All right? I don't know. I'm just trying to make this look like it's curved. But the point is here, there's our domain. This is a subset of R3 in this picture. This is just an example. And so what's our function going to do? Well, our function is going to assign to every point in this blob. So this could be just the surface or it could be the solid blob. Doesn't matter, right? It's just some domain in three-dimensional space. And our function is going to assign to each point on here a real number. So a real number that's in a different dimension here. So we'll call this the w-axis. But it's going to assign another real number. So again, every input is going to have its own output. It's a function, right? For every input, there's exactly one output. And yeah, so that's the way that it's going to work. We'll talk about graphs of these things a little bit later. And in general, we're only going to study the graphs when the domain is in two-dimensional space. But all right, so for our first example, I'm going to give us a function here. This is a function of two variables. So our function f of x, y, in this case, is going to be given by this formula, x plus y plus 1 over x minus 1. And the question here is, can we evaluate a couple things? So I want to do two things. Can we just evaluate it at a point, just so we see how it works? It's very straightforward. But let's evaluate f at the point 3, 2. And then 2, can we find and sketch the domain? So we're going to see that the domain is going to be a little bit complicated, more complicated than we're used to. So we're going to actually want to sketch the domain. Find and sketch the domain of this function. All right, so for the first item here, number 1, like I said, it's very straightforward. F of 3, 2, it's exactly what we would expect knowing how functions behave in Calc 1 and Calc 2. If the coordinates here are x and y, you put in 3 and 2, they just take the place over here. You just swap them out, right? So this one's going to be 3 plus 2 plus 1, over x minus 1. X is the 3, right? So 3 minus 1. And so just make sure that you match up the variables with the actual numbers in the slots here. And so when you work this out, this is just square root of 6 over 2. That's it, right? So that's a value there. But what that means, for one thing, is that the 0.32 is definitely in the domain because we got an answer back, right? We plugged in the 0.32, we got back an answer. And so therefore, this is a point in the domain, and this is the corresponding output of the function when the function is applied to that point, 32. All right, for the second question, we need to do a little bit more work. So let's write down the equation again. I mean, it's right here, but let's write it down again. So f of xy is equal to the square root of x plus y plus 1, all divided by x minus 1. And this is a rational function, so it has some restrictions, right, or some constraints. So let's write them down. What are they? Well, the first constraint that we see is we have a fraction, and so the denominator of a fraction cannot be 0, right? So x minus 1 can't be 0, and this tells us then that x cannot equal 1. So x not equal to 1 is one constraint on the domain of our function. All right, the second constraint comes from the square root, right? The square root, what's underneath the square root, has to be non-negative. So x plus y plus 1 has to be greater than or equal to 0. And so that's the second constraint. So x cannot equal 1, and for all other x values, this inequality has to be satisfied. All right? Like I said, we want to try to sketch this domain in our two-dimensional domain plane. So one thing that we might do is rearrange this to solve for y. So we could write this as y should be greater than or equal to negative x minus 1. And now we can try to sketch the domain. So our domain, again, lives in two-dimensional space. Right, lives in the xy plane. And I'm just going to put a couple of tick marks here in all directions just to give us some guidance of where we're working here. Here's x equals 1 though, and that's definitely not allowed, right? That was our rule. X cannot be 1. So we can't have this number, and we can't have any points that lie on the vertical line that passes through x equal 1. So I've drawn it as a dotted line to show that that is not allowed, right? On the other hand, what about this one? This is y greater than or equal to negative x minus 1. Well, the equal to part means that y can equal to all the points on this line, right? This is a line, y equals negative x minus 1. So it has a y-intercept of negative 1. It has a slope of negative 1, right? So it's going to be the line that looks something like this. And I'm being very careful as I approach this dotted line because of this constraint, I cannot equal, x cannot equal 1, right? So at this point, x cannot equal 1. All right, but all the other points on the line are okay. And then we are allowed to have some more points, right? So all the points for which the y value lies above this line in the vertical y direction. So all the points that lie up here are in our domain, again, except for the points that lie on the vertical line x equals 1. All right, so after all this analysis, what we found then is that this is our domain geometrically. It's like a half plane, but it's then separated by this vertical asymptote where x equals 1. That is not allowed. Okay, so that's how we can find and then visualize the domain of the function. This is just the domain. This is just the domain, right? This is not the range of the function, just the domain. So that's it. That's what we've got right here. All right. Before we go on, I'm going to let you guys do an example on your own. I want to give one more definition. So, definition now. We talked about this just being the domain. So especially for a function in of two variables, a function of two variables, its output is a third variable, right? And so the graph of such a function will live in three-dimensional space. The graph itself lives in three-dimensional space. And so here's what we want to define now. So the graph of a function f that maps from some subset D in R2 to the real number set R. This is the set of all points. So it's the set of all points in R3 that satisfy the following. I'm going to write this in set builder notation. I'm going to give it a name. So gamma is the Greek letter for G. So gamma f means the graph of f. Actually, let's write this like itself in function notation. So gamma of f. The graph of f is equal to a set, right? It's the set of all points x, y, and z such that x and y are in the domain of f. So that's just the set D, right? And z is equal to f of x and y. All right? So if the function is well behaved, if it's continuous and it behaves, you know, maybe it's smooth in some sense, which we'll define it as we move forward in this chapter. But if it's well behaved, then the graph of our function is going to look like a surface. Okay? So there's kind of two things going on here. We'll have our xy plane, and this is where our domain lives, right? So maybe our domain looks kind of like this shape down here. This is just in the plane. This is the domain in the plane. And then the function itself, what's it going to do? It's going to assign a value to each point in this domain. So maybe at this point right here, let's make it blue. Maybe at this point right here, the function is going to assign a value that corresponds to this height, right? So this height over here is going to be given by or determined by the function. Okay? And this is going to happen at every point in the domain, and you can think of the function as kind of mapping the domain up to the surface in 3 dimensions, okay? And so I'm just going to try to sketch something that looks like this. And so the idea is that this surface should be sitting directly above, so this should be gamma of f. Should be sitting, all the points on the surface should sit directly above corresponding points in the domain. All right, so again, it's just a rough sketch here. I just kind of made this up. But the idea is that this green surface is sitting directly above the red domain, the entire set here that forms a domain. And then the blue lines just show how the height is determined by the function itself. All right, so, and by the way, this could sit below the xy plane. I tried to make it so that we could visualize it easier. I tried to draw it like this, but now I've added so much to the picture that maybe it's not so clear. All right, but this is the idea. So at every point in the domain, a height is assigned, and that height can be thought of as a z-coordinate. The graph is then, in this case, if the function is very nice and well behaved, it's the surface that sits directly above or below the domain itself in 3-dimensional space. All right, so that's with the domain embedded in 2-dimensional, as the 2-dimensional portion of 3-dimensional space, right? All right, so here's one for you guys to try. This is number 4, item number 4. What I would like you guys to do is take a moment and try to find and sketch the domain of the following function, and then sketch the graph. Sketch the graph for this function. If you know, just give it your best shot, and then come back after the pause, and we'll finish it off together. So this function is g of x equals the square root of quantity 9 minus x squared minus y squared. So give this one a fair shot, and I'll see you guys back here in a moment. All right, let's see how this one works out. So this is, again, a rational function. It's a square root function. And the constraint here, if we mirror kind of what we did before, is that what's inside the square root has to be non-negative. So 9 minus x squared minus y squared must be greater than or equal to 0. And then what we can do is kind of rearrange, right? And we can write this as x squared plus y squared should be less than or equal to 9. Or, of course, that's x squared plus y squared should be less than or equal to 3 squared. And now we can see that our domain in the xy plane is going to be a circle of radius 3. So that's the equals part. circle of radius 3, and then it's everything inside the circle. So it's actually a disk, right? It's a disk of radius 3 centered at the origin. All right, so we get, again, the circle, but not just the circle. Because of the inequality, we get the entire disk of radius 3 in the xy plane. So there's our domain. All right, it's been found and sketched. Now the question of the graph is a little bit more complicated, right? So now that we know what the domain looks like, we know that that's what the xy plane portion of our graph will look like. So we can like kind of draw our xy plane this way. And like I said, we know that in the plane, this should be circle of radius 3, right? Actually a disk of radius 3. So there's our domain. And the next question becomes, what happens with the height, the z component, right? Well, to do that, we can remember, all right, the way that this is defined, the graph is defined, is that it's all the points for which z equals g of xy. The height is equal to the output of the function. Well, we can write this then as z is equal to 9 minus x squared minus y squared. And if we square, this is just positive, right? So z is positive in this case because the square root is positive. If we square both sides, we can write this as z squared equals 9 minus x squared minus y squared, and then maybe just remind ourselves that z is non-negative. All right, and at this point we can rearrange, and we can write this as x squared plus y squared plus z squared equals 3 squared, and again, constraint that z is non-negative because that's where it came from with the square root, right? It was the positive square root only. So there we go. And so what's this? Well, this is a sphere of radius 3. So this is the sphere of radius 3, which matches up with the circle of radius 3 down below. It's not going to be solid, right? It's going to be just the surface of the sphere of radius 3. And so in one way you can think about this is, okay, when x and y are both 0, then z has to be 3 in order for this equation to be met, to be satisfied. So this center point gets pushed up to 3, and then as you move outward toward the edge of the circle, right, you're going to end up with the upper half. So you get the upper hemisphere of the sphere, but you just get right, you just get the surface of the sphere. So all the points in this red disk that were the domain get kind of pushed up to form the surface of the sphere. So this blue graph here, this is the graph of G. And by the way, it leaves these points on the boundary, it leaves them alone. So there you go, there's the graph of this function. This function, its graph is a hemisphere. All right, using the same idea, same thought process, we can think about the following function. So this is item number 5. I'd like you guys to try this one on your own as well. So this time I want you to find the domain and the range. So we didn't talk about the range of this function, but the range up here of this function, right, it takes in z values between 0 and 3. So the range of this function is just 0 to 3. Right? And we could have checked that just by looking at the function itself, just by checking, right? Square root of 9 is going to be the biggest number, and then as you work your way down, square root of 0 would be the smallest number, and it takes on all the numbers in between. So we could have done that before we sketched it, right? But the graph came out of it. All right, find the domain and range of this function, and then sketch a portion, at least, of the graph. All right, so this one, the function is going to be given by h of xy is equal to 4x squared plus y squared. All right, so take a moment and try that one on your own, and I'll see you in a few seconds. All right, now that you've had a chance to try it, let's see how you did. This function, the domain of this function is going to be the entire real plane because there are no restrictions, right? No constraints as far as the domain is concerned. No constraints, and so this means that the domain is actually equal to all of R2. There are no bad points. The range, however, is constrained, and that's because the x and the y are both squared, and so the range of this function is never going to give us a negative number. It will give us 0, right, if x and y are both 0, but beyond that, it's only going to give back positive numbers. So the range of this function is 0 to infinity inclusive. So the half line. So it's going to be the upper half of the space, right, where the graph lives. And then the question of how do we graph it? Well, so again, we don't have to graph the domain because it's the entire real plane. But what we should do, right, is consider how do we graph it. So we can, as far as the graph goes, we can use what's called the trace method, which hopefully you remember from Calculus 2. But if we set z equal to 4x squared plus y squared, then we can take some traces of this. Okay, these are called traces. So I'll show you how this works with this function, and then you can try this on your own with some other functions. But the first trace that we'll choose is, let's choose the trace y equal to 0. If we take the trace, just means that we're going to look at a restriction, right? A restriction of the surface. If we zero out y, what's going to happen to this equation? Well, it's going to be z equals 4x squared. And we know exactly what that is, right? That's a parabola. So that's a parabola which opens very quickly. It's got 4, right? So it opens very quickly. Its vertex is at the, actually, its vertex, I'm going to do it this way because that's going out of the screen in the back, right? So its vertex is at the origin, and it's pretty narrow compared to a normal parabola, which, you know, you can't tell from this. What if you take another trace? What if you say, all right, take the trace when y equals 1? Well, look what happens now. Now you have the equation z equals 4x squared plus 1. Well, that's the same exact parabola, just shifted over so that it's sitting above this point, right? Y equals 1. That was part of our constraint. Y equals 1. The height is equal to 1. There's our new vertex, right? And so otherwise, it's the same exact parabola. So it's in a parallel plane. It's just been shifted over and up at the same time, right? Over and up at the same time. All right, well, so there's two traces that are parallel to the xz plane. One of them's in the xz plane, the other one's parallel to it. What we can do then is take traces that are parallel to the xy plane, or we can just look at the xy plane. So take the trace when x is equal to 0. This equation is going to be z equals y squared. Well, that's also a parabola, right? But this is a parabola which is not stretched out. It's not stretched like the other one, right? So it's going to be a little bit wider, and it's going to live in exactly, so it's supposed to go through that point, and it's supposed to be a parabola. So excuse my drawing, right? So it should look something like this. So there's the blue one, right? Where it should go right through. It should share this point. And then it's a parabola that's a little bit wider than the one that's in the opposite direction here. Again, because it's not scaled. It's just z equals y squared. All right, but it goes through the origin. It opens upward. Looks exactly like this. And at this point, we can kind of see exactly what this thing is going to, what kind of shape this is going to make, right? Because you can imagine sliding the red parabola. Remember, the red parabola, as we change the y slices, it just shifts it up and down, right? Up and down as it moves along. And so really what's going to happen is the red parabola is going to slide along the blue one, and it's going to fill out some kind of a shape. But for the sake of our trace methods, we can take the trace when z equals something. Notice if you take, because of our range, right, z can't be negative. And when z is 0, we just get the vertex. So what if we take, say, z equals 1, right? This height of 1 right here where we already have one of these points. Well, if we take this slice or trace, then this equation will be 1 equals 4x squared plus y squared. All right? And now this is an ellipse. So this is an ellipse. That's an ellipse. This was another parabola, right? Parabola. So this is an ellipse. It's going to go through right like that, right? So there you go. There's an ellipse. The idea here is that it is stretched more in the y direction actually, because it goes all the way to 1. It only goes to 1/2 in the x direction. So it's stretched kind of twice as much in the y direction as it is in the x direction. And as you continue to take these traces, you'll see that all these different points pass through ellipses that are all the same ratio, but they get bigger and bigger and bigger as we move up in the z direction. And so this shape it kind of looks like a bowl, right, connected by these ellipses. And so this is called an elliptic paraboloid. Okay, so hopefully again you remember this from Calc 2, but it's an elliptic paraboloid. And that's the graph of our function, right? So all the points in the plane, as far as the function is concerned, all of the points in the plane are mapped up to a point on the elliptic paraboloid. All right, so this is a point in our domain, and this point right here has coordinates x, y, and then h of xy. All right, so that's how graphs work. That's the role of the domain and the range. Not a whole lot of calculus yet, but this is the idea though. So we need to get used to this before we try to do calculus with these things. So these functions that we've looked at, these last two functions, are very nice. Their graphs are smooth, like super smooth, right? They don't have corners. They're very continuous. They're very nice, right? So these are some good examples. All right, let's look at one more topic before we call an end to this lecture. And so this we'll call item 6. We'll start this one with a definition. So again, we're going to think of a function of two variables. So let's let f map a domain in R2 to some real numbers. Again, I'm not worried about the range as much as I am about the domain. So when I write this, I'm going to be very clear about where the domain is, like exactly what the domain is, D. The range is just somewhere in R. And like we saw in the last one, sometimes you have to find it separately. You're not given as clearly the information, right? So the range is important, but the domain is somehow more important. Okay, so here's our function. It's just some function over a domain in two-dimensional space. So it's a function of two variables. Then the level curves. This is what we're defining here. The level curves of f are the plane curves that satisfy the equations f of xy equals k for each k in the range. So I just said it's not as important. It is still obviously important. I'm defining this by all the k in the range, right? In the range of f. So we define this by all the k in the range of f. So the idea is that for each fixed k in the range, there is one level curve, a level curve with that height, right? So there's one level curve, and then we map all the level curves on the same plane, in the same xy plane, and of course they're going to be mapped inside of the domain somehow. All right, so the graph that shows all the level curves on the same, or a number of level curves on the same set of axes is called the contour map of f. So the graph that shows many level curves of f on a single set of axes is a contour map of f. Okay, so let's go back to our function from before. So we'll do this as our example here. Our semi-sphere, right? So the function, remember, was g of xy is equal to the square root of 9 minus x squared minus y squared. All right, and I want to try to sketch the level curve, some of the level curves of this function. All right, so let's sketch some level curves. Let's start from the bottom and work our way up. We already know what the graph of this looks like, right? We already graphed it. It's the semi-sphere, the upper hemisphere, right, of the sphere of radius 3. So the heights, remember, I'll write this down here, but our range for this function was from 0 to 3 inclusive, right? Everything in between, nothing outside of this range. So there's our range. So we only want to pick values in here. So let's just pick the level curves k equals 0, 1, 2, and 3. And let's see how these match up. And then, you know, if you need more information, you can always add values here as long as they're within the range. You can always add values to get a better idea of what the level curves are doing. So I'm going to color code these. Let's start with k equals 0, right? So the way that this works is the k goes here. So this is going to be 0 equals the square root of 9 minus x squared minus y squared. All right? Square everything, rearrange. We end up with exactly our circle of radius 3, right, from before. So if you rearrange this, this equation satisfies this inequality, or this equality right here, right? So when k is equal to 0, we get the circle. Pretend it's a circle, not a very good circle. So we get the circle of radius 3. All right, but again, that's k equal to 0. All right, as we scroll up again, does that make sense? Yes, the circle of radius 3 is at a height of z equals 0 on the graph, right? As far as the graph's concerned, when the height is 0, we get this circle of radius 3. All right, let's go up to k equals 1. When k equals 1, our equation is 1 equals the square root of 9 minus x squared minus y squared, right? Square both sides, rearrange. What do we get? This one becomes x squared plus y squared equals 8. And 8 is the square root, so it's 2 root 2, right, squared. 2 root 2 squared. So this is going to be a circle of radius 2 root 2, which is a little bit less than 3. It's like 2.8 or something, right? So it's pretty close out here. 2 root 2 is pretty close. Again, pretend it's a circle and that it's concentric. And so this one is 2 root 2, and that's when k equals 1. All right? So again, as we scroll up, we went not very far away from the boundary of the circle. We went up a whole unit, right? A whole unit very quickly. And so as you can see, the edge around the outside of the circle, it's very steep, right? You can imagine the tangent lines to any curves of these circles around the edges, around the boundary, would be vertical. So this is changing the heights very quickly from, you know, near this point on the boundary. And as we move along this thing, we move up the height of the graph, we'll see that we didn't get very far in the x or the y direction before we got up one whole unit, right? One whole unit in the vertical direction. Okay, then we'll go to 2 then. Next step, right, is go up to 2. So we'll do this one in green. When k is equal to 2, let's see what happens. So 2 is equal to the square root, 9 minus x squared minus y squared. Square it, rearrange. This time we get x squared plus y squared equals 5, right? And so obviously 5 is just square root of 5 squared. Square root of 5 is still a little bit bigger than 2, right? It's a little bit bigger than 2. So it's maybe around here. So the idea is that it should be a little bit further away from 2 root 2 than 2 root 2 is from 3. All right, so again, this is square root 5, and this corresponds to a height, a level curve of k equal to 2. Again, we scroll up. Well, in that next unit that we moved up from 1 to 2 in the height, notice it's flat. The curve has kind of flattened out a little bit, and we can make a little bit more progress toward the center, toward the z-axis, right? As we're hiking, if you think of hiking up this dome, but we're still pretty far away, right? So it's still pretty vertical out here. It's getting a little bit less vertical as we go, so we made a little bit more ground as far as the radius is concerned, as opposed to the height, right? So, all right, what about the last one? Well, I chose to just use 0, 1, 2, and 3. Let's see what happens when we use 3. Well, if k equals 3, you can probably guess what's going to happen, right? 3 is equal to the square root of 9 minus x squared minus y squared. And if you rearrange this, you end up with x squared plus y squared equals 9 minus 9, or 0. And so k equals 3 just gives us the circle of radius 0, or the point, right? The point at the origin. And so that is the point right here at the kind of the vertex of our dome. And so if we go back here and we try to plot these level curves, the red was the boundary. The blue one, I did this in blue, so I'll do a lighter blue. Lighter blue is a height of 1, right? But it still looks very, very close to the boundary down here. The next one was green. That's a height of 2. So it's getting better, right? And then from green to pink or to magenta here, the magenta point is right at the origin, right? So of the circle. So, but this one, so the idea here is that from this height of 2 to 3, it becomes very flat, and you make a lot of progress in terms of the radius, right? You can reach the peak in some sense of this dome. So the whole idea here is that the level curves can tell you something about the graph and vice versa. Because if you were to go back to this graph and you were to slice kind of horizontally at each of these curves, and then even more, and then project those slices down to the base, you would get exactly this graph. And so the idea is that the curve is changing more steeply. It's very steep when the level curves are close together, and the curve is more flat. It's changing more gradually when the level curves are spaced out more, especially if the level curves are spaced out evenly with respect to the height, right? So each one of these level curves represents one unit stepping in height, right? And so when they're close together, that step in height has to be very steep, and when they're far apart, this step can be more gradual, right? More gradual. And so these level curves and this contour map can tell us a lot about the geometry of the graph, the surface itself. All right, so we're almost done. I mean, we pretty much are done. The only thing that we should say is what happens if, the question we should ask, I should say, is what happens if our function is not a function of 2 variables, but of 3? All right, so what happens, can we do the same kind of analysis that we just did, right? So if f maps a domain in R3 to a real number, right? If it's a function of 3 variables, then level curves become level surfaces. So they're no longer curves, right? So level curves become level surfaces in R3. In R3. All right. And so just for an example here, I won't write out the entire thing, but here's an example. If f of x, y, z is equal to x squared plus 2y squared plus 3z squared, then this is a function which takes in points in space, right? And again, domain is not restricted here. All points are allowed to go in. There's no constraints. The output is a fourth real number. So it's hard to imagine what this could be, right? So how can you visualize what this function is doing if it's working in 4-dimensional space? We don't live in 4-dimensional space. We can't think in 4-dimensional space unless we include, say, time or maybe color as a 4th dimension. So in terms of just spatial dimensions, though, we don't work in four-dimensional spatial dimensions, right? So what can we do? Well, we can do the same kind of idea of taking level surfaces, and we can say, all right, here's our domain. Our domain is all of 3-dimensional space. It's all of R3. All right, so x, y, z. And then we can just take level curves. When k is equal to 1, this is an ellipse, right? It's an ellipse that is stretched more in the z direction than the y and more in the y than the x. So it's going to be stretched quite a lot in this direction, an ellipsoid, I should say. It's an ellipsoid. And then it's stretched a little bit less in this direction. All right, and so you get something like this. And as you build up, so to say k equal 2, then what's going to happen? Well, you're going to get nested ellipses. It's going to look like, say, nested dolls or something. And these things are just going to, it's going to be hard to tell, right? But as you work your way out, then these surfaces are going to work their way out as well. All right. And again, it's hard to see exactly what's happening, but the whole idea here is that these are equations of ellipses, right? And so you end up with nested ellipsoids. Nested ellipsoids for this example. All right. And so for other examples, you might get nested cones, nested hyperboloids, a cone nested between certain types of hyperboloids. You know, there's all kinds of different shapes that you could get. But the different level curves will divide up the domain space into, in this case, into infinitely many surfaces, which all have pretty much the same shape, right? But they have different geometric properties as far as their size, their, you know, arc length, surface area, stuff like that. Okay? So, but the basic idea here is that the level curve idea does extend to three-dimensional space, but it extends as level surfaces because you need the third dimension, right, of the domain. All right, let's leave that lecture here, and I'll see you guys in the next one.